Time for non-detrital rocks. I'm calling them chemical sedimentary rocks because no matter whether chemistry ripped them apart into ions, transported them elsewhere, where they deposited as nice little grains, or an animal just kind of ate them up, put them in their body, and then pooped them out, or grew bones and shells, doesn't matter, they all come from chemical means. And we classify them using just the mineral composition, so what are they made of? And then also the texture, the size, because the grain size is going to tell us, was there enough of the materials in there to make big grains? Were they built inside of a shell, on the outside of a shell? What's the deal? So let's have a look. We're going to start with limestones. We're going to start with the small ones. These things are made of mud. It's macritic mud. It's calcite mud. You might see a glimmer on a rock every once in a while, but hey, you put your hand lens to that thing, you're not going to see a crystal. You're not really going to see habit. You probably might see a crystal face every now and then, but they're all about the size of very fine silt to clay-sized particles. Like regular shales and mudstones, as they fall to the ground and they gather up and they're compacted, they don't have cement. It's just muddy squishiness. They have this curvy fracture, conchoidal, kind of reminiscent of obsidian and other glassy things. And as they precipitate like snow and they are fine silt and clay size, you should be able to come up with the energy that's needed for deposition. Clay sized. What energy is that? Where does limestone form? Oh yeah, the ocean. Definitely. And where does mud go? Well, it's carried way far away from the beach. It'll probably be back down behind the reef, where it's a little bit cooler, a little bit calmer, no real wave action. Here, this is probably one of the most crystally type of micrite rocks you're gonna see. It doesn't look earthy anymore because we're looking at a fresh surface. But if you put your hand lens to that, you're gonna see very fine silt or clay-sized particles and little types of glimmers. When we zoom in, gray, yucky stuff, very small grains. These grains here, they were made by something else because these things are large crystals. Crystalline calcite, what a segue. So this is precipitation that is occurring maybe inside a shell, around a shell, or it's precipitating freely because the waters are warm, the pH is low, and calcite, as you recall, cannot precipitate in super cold waters because super cold waters can hold more acid. And if you can hold more acid, then you're going to be able to dissolve calcite crystal. The best reefs are in places like the warm waters around Australia or down in the Caribbean. We don't really go to Iceland to see cool reefs because calcite can't precipitate there. This is what a crystalline rock will look like, and you might say, why is it all white? And what's the black stuff? The black stuff, those are shell fragments that have been remineralized with metals, and I'll prove it to you. Cross the poles and they remain black. Except cross the poles and all that white grainy stuff and the tan grainy stuff, we can begin to see faint pinks, faint yellows, faint blues, faint greens, faint oranges. All of these are the pleochroism of calcite. Another really cool thing about this image is take a look around the fossil fragments and you'll see finer calcite grains growing out radially from the fossil fragments, much like here. So those small calcite fragments were starting to recrystallize when this rock, these grains, underwent the pressure and compaction and underlithification. Sweet. There's very little micrite in a crystalline limestone because it's been washed away. These calcite grains are large, so they can be deposited in higher energy environments. This is a pretty decent crystalline limestone. The gray, that's calcite. The tan, calcite. The white, yep, you guessed it. Well, based on the micrite and based on the presence of larger grains, we're definitely talking something much more closer to reefs. So just getting a pure crystalline calcite limestone, that's kind of difficult because oftentimes we're going to find other kind of grains in there like sand grains and fossil grains, broken fragments, but we're definitely in a moderate to moderate high energy. We could be moderate low. We could be moderate low. We'll go moderate low too. When you do mix crystals and micrite mud, Well, the micrite mud is usually compacted inside fossils or in between crystals, grains of calcite, or it's surrounding pellites, or it is pellites. And pellites, me pointing out this kind of cylindrical things in the second slide saying, those aren't micrite because that was a hole, that was a pore, there were crystals regrew. Well, pellites are poop. The crystalline calcite is here. It's the white and it's the lightish gray. The gastropod here has both crystalline calcite in here, but it also has this gray stuff. This gray stuff is the mud, is the micrite mud, and that means that the rest of this grayness is mud too. The blue, these are fractures, and so there's no rock in the squiggly black line here that we see. This is called a stylolite. This is mostly metals, pyrite and magnesium oxides and hematite, and it forms when the rock comes under intense pressures. Here we have a gastropod, or a snail shell, and the snail shell, once again, has grains of both calcite, like this, but also has these other things. It's got pellites and micrite bits. Whoa, that's a really big pellite. Jeez. And here's some pretty big crystal grains. The combination of both micrite mud and crystalline calcite is telling you that probably the large grains are being brought down into the small grains. So the crystals of calcite probably precipitated elsewhere along with these shell fragments, and then were brought down into the micrite mud area. Fossiliferous limestone, or skeletal limestone, is made of a bunch of skeletal fragments. Now, no living organism with any bit of respect would gather themselves all clumped and huddled together. Now, these are death assemblages. When we really see skeletal or fossiliferous limestones, we're looking at a death assemblage. And geologists love death assemblages. It allows us to see what all beasties were living together at one time. We can figure out who ate whom. We can figure out the populations of these organisms. It's a great thing to find death assemblages. It could tell us whether there was a big storm or if it was climate change. It really helps us piece together the history of the Earth. Just tons of snails have lived across the surface of this Earth. Because of the size of fossil fragments, the energy that they like to hang out is moderate high. Inside these shells, the only thing that's going to precipitate are crystals of calcite. Fancy limestones. Coquina, bunch of broken shell fragments. These usually occur at high energy environments. Places where waves are taking the shells of dead beasties, smashing them into a cliff edge, or there are intense waves on the beach, smashing the shell fragments to bits as well. We can see all sorts of shell fragments in disarray, a little kind of clammy thing here. This was one side of a shell fragment. This was one side of another shell fragment that apparently was a wishbone of a turkey. No, don't believe that. That's not true. Oolitic limestones. Let's see where this link goes. Apparently there's a great video game called Oolite. This link goes to a Wikipedia page where you can find out more about ooids, if you would like, and how they form. Taking a look at a photomicrograph, calcite is growing radially with a pellite over here on the left. Sand grain almost smack in the middle, looks like another pellite or crystals of calcite down here. And this star radial pattern is telling us that we didn't really cut across the nucleus. This is either above or below the nucleus. Dolostone. Dolostone is very, very, very cool for how complex and confusing it is. It is limestone, but with an extra magnesium and an extra carbonate thrown in there. And incompatible means it doesn't want to bond with anything. So how the heck did we get a magnesium bonded in here? That's the big question. To test for dolostone, if you just drop acid on the rock, you won't see a fizz. It'll be the same reaction as if you were to drop acid on a sandstone or drop acid on a clay stone. But if you freshly break the surface, you'll be getting a new surface where oxidation has not occurred, where the carbonates are free to fizz away. The formation processes of dolostone are twofold, two possibilities. The first one is just standard limestone that has been altered during diagenesis. Extra heat during or after lithification, but we're just not really sure. Chemically, mathematically, it works out that if very warm waters pass between the grains and are forced through the calcite, there can be an alteration, and we can take CaCO3, smack another magnesium and another carbonate into it, and voila, we have dolostone. However, observing this process is really difficult. The other option is biogenic. Super salty waters permit the growth of this bacteria that likes to grow in huge colonies, in huge mats. The only problem is that even though it builds dolostone, or CaMgCO3 too, as its shell, if we're looking at dolostone in the past, why doesn't it have a concentric growth pattern and growth rings and just look mound and mound and mounded like the algal mats that we see growing today? It's really confusing. It's a great area of study too, though. Finally, enough of the calcium carbonates. Here we are at evaporites. Evaporites tell us where the oceans existed in the past when we don't really have a whole lot of other rocks. Come to a basin and find a whole bunch of salt. There's only one way that it could have gotten there, and that's through evaporation of ocean basin. Oftentimes, many biogenic processes go in here, and there's a whole bunch of sulfur hanging around. This sulfur bonds with calcium and water to make gypsum. A thin section of gypsum will reveal that the grains constantly reorient and change their position, which is what's causing this pleochroism here. And then last but not least, the biochemical Sed rocks, the ones that had a direct form from organisms. The first is chert or flint. This has a cryptocrystalline texture. We know that it's silica because we'll powder the bejesus out of it. We do all the tests, and it is SiO2. However, when we look at it under the microscope, we can't find a single gray or whiteness. Because remember, quartz in cross poles is supposed to look gray or white. And this looks nothing like it. So it's cryptocrystalline. These form from the reorganization and the remobilization of silica inside of a limestone or inside of a shale, and it's reorganized from sponge spicule. If you've ever touched one and then you break out in a rash, your body's having a reaction to the tiny little like silica needles that give sponges their framework. Last and least, coal. Coal comes from a whole bunch of dead plant matter that's squished together, and from being squished together, it looks like it's got a crystalline texture. It's shiny, and when we look at it underneath the microscope, we can see areas, locations that were once plant remains, and they're all fragmented together. There's even some coals that as you start to peel them apart, you can tell you're peeling apart very carbon-rich leaves, which I just think that's so cool. We also find oftentimes keratin inside coal, that waxy stuff in oil shales. All right, as usual, bring your questions to class. See you at school.